We're now going to talk about the proximal point algorithm. We've seen the prox operator in the lectures on proximal gradient. But now we're going to talk about properties of the prox operator and even investigate it as an algorithm in and of itself. So the problem I'm always trying to solve is minimize f of x. And recall that the prox operator I'll put a hat here, is defined as the argument over x of f of x plus this proximal term, which keeps you not too far from the argument of the prox operator. 1 over 2 lambda times x minus x hat. And the proximal point algorithm is just simply to iterate this operator. Proximal point algorithm, which sometimes I'll just abbreviate, is simply to write xt plus 1 is equal to prox step size times f of xt. And so I want to know when is this a good idea, what it looks like in the dual, and what is its relationship to things that we've already seen. So things that perhaps we understand better. So I want to know, when is this a good idea, and what are properties? So when is this a good idea? Again, the reason that that's a natural question is that you look at this, and even going from xt to xt plus 1, it looks like it involves a problem that's certainly related and therefore potentially as hard as solving my original optimization problem. I need to minimize f of x plus a quadratic. So certainly, generally, this isn't going to be something that's going to be easier. And but aside from that, basic properties we could ask are, is this even guaranteed to converge? So in fact, we've already seen that answer, and we know that it converges, and we also have an idea of rates of convergence. We'll get to that in a minute, but we've already done that work when we analyzed proximal gradient algorithm. So this is what I mean by properties, and we'll also want to look at what does this look like, what properties does it have when we apply it to the dual. This is a roadmap of this in the next lecture. Okay, so our proximal point algorithm. So one thing that we can observe right away is that proximal point algorithm applied to a linear approximation of f just gives us back gradient descent. So specifically what I mean is if f, I'll superscript 1 to denote first order Taylor approximation of x, if this is equal to f of xt plus gradient or subdifferential, it doesn't matter, but just to make the point simpler here, x minus xt, this is a first order approximation of the function f at the point xt. And if you now write xt plus 1 is equal to prox of the function f1, my linear approximation at xt, just check this, that this is equal to xt minus gradient of f of xt. Just check to make sure that you remember the mechanics of this. So proximal point algorithm can be seen as something that can return gradient descent. Also interesting to apply it to the quadratic. So PPA proximal point algorithm applied to a quadratic approximation, second order approximation of f, in other words, f2 of x is equal to f of xt plus the linear term plus the quadratic term this gives something that is familiar, though we haven't seen it exactly. If xt plus 1 is equal to prox lambda f of 2 of xt, this is something that looks like Newton but isn't quite Newton. It's called modified Hessian Newton, and it's basically using a Hessian that is regularized by making sure that none of its eigenvalues are too small. Which you would want to do because you're potentially inverting. So this looks like xt minus, not quite the inverse of the Hessian, but this plus this multiple of the identity, inverse times the gradient of f of xt. And so here you can see that the larger lambda is, it actually corresponds to something that's closer to a full Newton step. So there's no damping here, but rather when lambda is very small, it's really, you're really taking a step. You're really approximating gradient descent. So as lambda goes to 0, this approximates a step in the gradient direction with step size lambda. And as lambda goes to infinity, this approximates Newton, an undamped Newton method. And so this is called modified Hessian Newton. And it's also sometimes called the Levenberg-Marquardt algorithm. And probably like things in optimization, things have been discovered and rediscovered many times, so perhaps it has many other names as well that I'm not aware of. Let's continue on understanding properties of the proximal point algorithm. This is a slight aside, but really an important one, and an important one that links to a deeper understanding of proximal point as an algorithm or as part of a family of algorithms that are fixed point algorithms. And so we've already talked about the monotone property of the subdifferential. You can think of this as a generalization of that. So recall that f, we showed that if f is convex, this implies, no assumption on differentiability, that if y1 is in the subdifferential of f at x1, and y2 is an element of the subdifferential of f at x2, then y1 minus y2, x1 minus x2 is always greater than or equal to 0. And in fact, we also worked hard to show that, that the other direction is also true, so that in fact this is an if and only if condition. Which we called monotonicity. So I'll just summarize this by saying that this is monotone when f is convex. But we can generalize this definition to other things. After all, this subdifferential is really just a set. So we can generalize this idea. After all, this is something that maps Rn to, sometimes two arrows are used to indicate a set valued mapping. So in other words, this is a set that, again, could have more than one value if our function is not differentiable at a particular point. So this is all we have, and so we can replace this subdifferential with really any operator and define a monotonicity property. So t, single valued or possibly multiple valued. So I'll leave that possibility open. Is called monotone if it satisfies exactly the property that we have above. So operator T is called monotone if, again, I'm essentially copying exactly what I have written in the first line. If yi is an element of t of xi, then y1 minus y2, x1 minus x2 is greater than or equal to 0. Well, this is called monotonicity. For T, a monotone operator, a very important definition is its resolvent. And this is also an operator. The resolvent of an operator T is defined as identity plus lambda T inverse. T is a mapping from Rn to Rn, therefore its inverse is we can define it as well. So we've only seen one monotone operator concretely, namely the subdifferential. So let's plug in the subdifferential and see if we get something that's familiar. And of course, you can probably guess what we're going to see just by the title of all of these slides. And I'll even just write it as a proposition, though it's really just manipulation, and the only thing that we're making any sophisticated use of is this inverse property of the subdifferential, which we saw in our series on Fenchel dual. So the proposition says that actually this, if I plug in the subdifferential for t, this is exactly the prox operator. Prox lambda f of some point x hat is exactly equal to the resolvent, where I'm using f here, at x hat. So let's we can see that this is basically immediate by the work that we've already done. So so what do we have? If x is an element of I plus lambda subdifferential of f inverse at x hat, this is just equivalent to x hat being an element of I plus lambda evaluated at x. And now you can see what this is just by distributing this operator. There's no inverse anymore. So this is just equal to x plus lambda delta f, subdifferential at x. Now let's look at this and put x hat over onto the right. So this is equivalent in turn to writing that 0, so in particular I want you to look at this this part right here. So what I'm going to do is write this as 0 being in the subdifferential of something. So this is the same as writing that 0, what is in the boxes here, is the same as writing that 0 is an element of the subdifferential of f at x plus, and in order to get the subdifferential, I have to divide through by lambda, which is fine because I have a 0 here. So plus 1 over lambda times x minus x hat. But this is exactly the optimality condition for x being the Prox operator. This is exactly writing that x is in the argmin of f of u plus 1 over 2 lambda times u minus x hat. I'll just squeeze in one more line. This is exactly like saying that well, this is basically what we're trying to prove. So this tells us that this resolvent operator is exactly Prox. So let's see what relationship this has with gradient descent. We've shed some light onto this. So the proximal point algorithm is saying that again, xt plus 1 is equal to prox lambda f of xt. And we just said on the previous page that's the same as writing that xt plus 1 is equal to I plus lambda subdifferential inverse evaluated at xt. Let's carry this through a little bit more. And so this is the same as saying that xt is an element of I plus lambda evaluated at xt plus 1. I just used the inverse property, which is the same as writing that xt plus 1. Now I'm going to solve now for xt. Let me write this out here. This is xt plus 1 plus lambda delta f at xt plus 1. So writing out this, rearranging and solving for xt plus 1, I find that xt plus 1 is equal to, let's just simplify this setting into where is an element of xt minus lambda times the subdifferential of f at xt plus 1. Let's rewrite, so if is not important, it's just to visually let us look at it. So if this is single valued, in other words, if our function f is differentiable, then this is just the gradient. And so what do we have? We get that xt plus 1 is equal to something that looks familiar, except it has a small difference. Xt plus 1 is equal to xt minus lambda times the gradient of f of xt plus 1. Right? This is the key difference. So note that what's gradient descent? Gradient descent is xt plus 1 is equal to xt minus lambda gradient f of xt. But that's not what we have here. So we have, so this is xt plus 1 versus xt. So this is why this is an implicit algorithm. And it's saying that xt plus 1 is equal to xt minus a gradient step, but the gradient is evaluated to where you wind up. So this, in addition to the notation that has an inverse, is why the proximal point algorithm is often called a backwards algorithm, whereas gradient descent is called a forward algorithm. So I'll write this down. So this is backward. Proximal point algorithm is called a backwards algorithm. Gradient descent is called forward. or a backward operator really. And gradient descent is called forward. Okay, so this is a nice interpretation of proximal point algorithm, and it helps us understand what it's doing. And we're going to see this. We're going to see this again. On the other hand, we also know that it's pretty close. They're pretty related. That we could say informally, in any case, that if lambda is small, then I plus lambda, delta f, gradient of f inverse, is approximately equal to I minus lambda delta f. This is an informal statement. And in that case, we can also see a proximal point algorithm as an approximation to gradient descent, or gradient descent as an approximation to proximal point algorithm. So this is, again, PPA operator, and this is the gradient descent operator. I next want to move to talk about the proximal point algorithm in the dual. So we're back to our setting of our primal and dual algorithm. Minimize f of x plus g of ax. This is the primal, and our dual is maximize minus f star of minus a transpose z minus g star of z. And I will call this function h. So this is h, and now we can try to understand what is proximal point doing if I apply it in the dual. In other words, if I just apply it repeatedly to h. We've been talking previously about gradient ascent in the dual, but now I'm going to use proximal point algorithm in the dual. So in other words, this is a maximization over z, minimization over x. So PPA in the dual is zt plus 1 is equal to prox lambda h. H again is this function I've underlined of zt. Let's write out the definition. Just by definition of prox, this is the argmin over z of f star of minus a transpose z plus g star of z plus 1 over 2 lambda times z minus zt squared. Note that I just pulled a minus sign through. So I'm using prox. Prox is a minimization here. And instead of max minus f star minus g star, I'm just making that a min of f star plus g star. So I'm minimizing a convex function rather than maximizing a concave function. This just spares me from having to redefine things for concave functions. Okay, so let's understand what this is here. So this is zt plus 1. I need to solve this minimization problem. As always, when we're talking about the prox operator, we write down its what are the optimality conditions. So the optimality conditions now tell me that 0 is an element of minus a times the subdifferential of f star evaluated at minus a transpose z t plus 1. So this is when zt plus 1 equals the prox, if this is the case, plus subdifferential of g star evaluated at zt plus 1 plus 1 over lambda, the 2 cancels, zt plus 1 minus zt. Again, I'm saying these are optimality conditions for zt plus 1 to be the optimal solution. And so I can now write down my update. Zt plus 1 is equal to, so I'm just going to solve for zt plus 1 here. So zt plus 1 is equal to, I'm going to multiply through by lambda, move everything, and then isolate this zt plus 1 on one side. I get zt plus 1 is equal to zt plus lambda times ax hat minus y hat, where x hat is an element of the subdifferential of f star at minus a transpose zt plus 1, and y hat is an element of the subdifferential of g star at zt plus 1. This should look extremely familiar to what we did in the previous lecture on dual decomposition. So here is what my proximal point algorithm in the dual looks like. And you can see that it looks a lot like a gradient step. Zt plus 1 is equal to zt. It looks a lot like gradient ascent. Zt plus 1 is equal to zt plus my step size times something. And that something is in the subdifferential. It looks like gradient ascent, but it's not gradient ascent because it's a subdifferential evaluated at the updated point. Exactly what we said on the previous slide, and why PPA, proximal point algorithm, is called a backwards operator as opposed to gradient descent, which is called a forwards algorithm. Maybe this is belaboring the point, but I think it's worth just doing again quickly what we had for gradient ascent, so gradient descent in the dual, just so we can crisply see the difference. So I'm gonna go over this pretty quickly because we've seen it almost exactly like this a number of times before. Minimize f of x plus g of ax. I'm just copying our general framework here. Again, the dual is maximize minus f star of minus a transpose z minus g star of z. And gradient ascent tells me that zt plus 1 is equal to zt plus lambda times something that is an element of the subdifferential of the whole thing, minus f star of minus a transpose z minus, sorry, zt, right? Minus g star of zt. In other words, I think it'll be easier if we write out, if I put something in this box here. So let's call this W. So that means that W is an element of carrying out, doing chain rule, a subdifferential of f star of minus a transpose zt minus subdifferential g star of zt. So W is equal to a x hat minus y hat, where now I have x hat is an element of the subdifferential of f star at minus a transpose zt, and y hat is an element of the subdifferential of g star at zt. So again, this is the key. This is the whole story here. And and so in particular, just to repeat what we saw before, x hat is an argmin of f of x plus zt transpose ax, and y hat is an element of the argmin of g of y minus z transpose y. So this is exactly what we saw in the previous lecture on gradient ascent in the dual. We see the two problems decouple. We see that we're solving subproblems which are exactly the Lagrangian. So this is different. So so now we need to figure out what we need to do now that we have proximal point. So now that we have subdifferential evaluated at zt plus 1. So okay, so back to our proximal point here. We've got again, just quickly writing down what we've seen. So we're maximizing f star minus a transpose z minus g star of z. Our algorithm is, our proximal point algorithm is zt plus 1 is equal to the prox of lambda h, where h is this whole thing that we're maximizing, zt, which is, again, by definition of the prox function, and the argmin over z of f star minus a transpose z plus g star of z plus 1 over 2 lambda z minus zt, which is the same as writing that zt plus 1, I'm still copying from the previous slide, the 2 slides ago. Zt plus 1 is equal to zt plus lambda of a x hat minus y hat. X hat is an element of subdifferential of f at minus a zt plus 1. And y hat is an element of subdifferential of g star at zt plus 1. So we would be in the clear if it were zt. Well, we wouldn't be in the clear, we would be back to just gradient ascent. Okay, so we're going to, so now let's take one step. Let's use our properties of Fenchel dual, the subdifferential being inverses of each other. So this is the same as writing that 0 is an element of the subdifferential of f at x hat, kind of doing a couple steps together. So I'm taking the inverse here and then also moving everything over onto the right. Plus a transpose zt plus 1. And similarly, 0 is an element of subdifferential of g at y hat minus zt plus 1. Okay, so how is this going to help us? So we could directly write that x hat is the minimizer of something, but that something would have a zt plus 1, which is, again, where we're going to end up. So that would be an implicit algorithm. So not going to help us directly. So what we're going to do is we don't like the zt plus 1. This is what's making our lives difficult in terms of defining an explicit algorithm. So what we're going to do is just plug in for what zt is, what zt plus 1 is. So we'll just plug in from star, namely zt plus 1 is equal to zt plus lambda a x hat minus y hat. So let's do that into our expression here. So now, plugging this in, our expressions become 0 is an element of the subdifferential of f at x hat plus, and now is where I'm going to plug it in. So it's a transpose times zt plus 1, which is equal to zt plus lambda a x hat minus y hat. And similarly, 0 is an element of the subdifferential of g at y hat minus zt plus 1, which is zt plus lambda a x hat minus y hat. And now let's look at this, and we can recognize, maybe it's helpful to write out one more step here, at least for this one. Subdifferential of f at x hat plus a transpose zt plus lambda a transpose a x hat minus y hat. And then this thing on the right doesn't need any further simplification. What do we do whenever we have 0 as an element of the subdifferential? We try to recognize this as the first order condition for an optimization problem. And that will allow us to characterize x hat and y hat. This is the same story that we've been doing. So, we're pretty close. So, for example, one thing that we've become very used to is looking at these two terms here. We know that if we only had these two terms, so let's ignore this for the time being. We know that that's equivalent to 0 being an element, to x hat being an argument of f of x plus z transpose ax. This is what we've been using for dual gradient ascent. But now we have this, and just looking at it a little bit, and actually it's easy to verify. You can check that that these two constraints together are exactly the optimality conditions for a coupled problem. So this is exactly the same as writing that x hat and y hat solve the problem f of x plus g of y plus z transpose ax minus y plus lambda over 2 times ax minus y squared. Maybe I'll just talk this through just to make sure it's clear. So we have this minimization problem over x and y, and x hat and y hat are optimal if 0 is, and you can just see what's going to happen. So the derivative with respect to x is going to give us subdifferential of f, g goes away, plus this z transpose A is going to be left over, which is the transpose of A transpose Z. So I've got that. That's this part. And then here, by the chain rule, I'm going to bring out an A, and a 2 is going to come down, cancel the 2, and so I'll have lambda times A transpose A x hat minus y hat. And then similarly for G. And sometimes you'll see this. We can rewrite this. We can rewrite this by observing that this cross term here, that this term really looks just like a cross term. So we can rewrite this as the argmin over xy of f of x plus g of y plus zt, that's exactly what we're going to bring in here, plus lambda over 2 times the norm of ax minus y plus zt divided by lambda squared. If you just multiply this out, you'll see the only way that these differ is in a constant term of zt squared. But because I'm looking at the argmin, we've played this trick a number of times before. If I'm looking at the argmin, I can add anything that is not a function of x and y. So as an argmin operator, these are the same. And these are called either one of these forms. Of course, they're equivalent. This is called the augmented Lagrangian. And again, looking at this first part, if I just had this, you can see that there is no coupling between x and y. And so this would decouple into the two problems that we saw for gradient ascent, namely just minimizing over x of f of x plus z transpose ax, and minimizing over y, and minimizing over y separately, g of y minus z transpose y. But now these don't decouple because of this augmented Lagrangian. So this is a connection between the proximal point algorithm and the augmented Lagrangian. We are going to talk about properties that it has. We're going to talk about convergence rate, and also when it's a good idea. And this is something that we're going to pick up in the next lectures.